Here I will discuss about multi-class classification. First, I will start with few applications or examples, then different approaches for multi-class classification like one versus rest approach, deep learning approach. Deep learning approach is the most widely used nowadays. So next I will discuss about output representation. How do we represent different output classes? How to calculate the class probabilities? Then why do we use softmax? Loss function. So loss function for multi-class classification is cross-entropy loss. So we'll see how do we derive the loss function or the cost function. So there are two types of cross-entropy loss, categorical cross-entropy and sparse categorical cross-entropy. We'll see the differences. And lastly, we'll discuss about inference. For a new test data, how do we get the output class? So few well-known examples of or applications of multi-class classification. Handwritten digit recognitions. So there is a well-known MNIST dataset available of handwritten digit images. So it will have images of 0 to 9 and we have to classify them as one of the 0, 1, 2, 2, 9, 9, one of the this 10 classes. Animal image classification. So let's say you are given few animal photos and you have to classify them as either dog, cat, lion, elephant, bird or any other animal classes. Email category prediction. So let's say you are given email text and you have to find out the type of the email, whether it's a work email, personal email, promotions or spam email. Next, fruit recognition. So let's say you're given fruit photos. So you can classify them as apple, banana, grapes, orange, pineapple. Any types of image classification is one example of multi-class classification. Language detection. So let's say you are given some text message and you can try to classify them based on the language, whether it is in English, it is in Spanish, French, German or Hindi. Sentiment with multiple emotions. So let's say you are given product review text and you can find out the emotions or the sentiment behind the text, whether it's a happy one, neutral, angry, sad one. So now consider you have this training data set x1, y1, x2, y2 till xn, yn. Xi's are the features, yi's are the labels for all I 1 to n. Xi's are d-dimensional because input will have multiple features. Each yi will belong to any of the classes C0, C1 to Ck-1. So in binary classifications we have seen there is only two classes. One is a success, one is a failure. We can get it as 1 and 0 or 1 and -1. Right? For multi-class classification, we have k classes, right? So yi's, the output levels will be either any of the classes. So we have to predict probability p of yi given xi from the training data set, so that for any new x we can predict its class. Now we need a classification over k classes here, right? So consider you will find the probabilities for each classes. So there are k classes C0, C1 till Ck-1. We are using 0 indexing here. Consider the probabilities for each classes are as follows: P0, P1 till Pk-1. P0 is the probability of class C0, P1 is for the C1 and so on. So these are the probabilities. So the sum of all the probabilities will be 1. Now the question remains how you will calculate the probabilities. So before going there, first discuss different approaches for multi-class classification. So the first one is one versus rest approach. So let's say we have the data set where we have 3 classes A, B, C, these 3 classes. So what we'll do here, we'll train multiple binary classifiers. So in my previous videos, I have discussed about logistic regression, naive-Bayes, KNN and all. So we know how to do binary classifications. So we will train multiple binary classifiers. Each classifier is basically one class versus all others. So let's see the example. We have three classes A, B, C here, right? So there will be three classifier, binary classifier. First classifier where one will be A versus rest, means B and C. Classifier 2 will be B versus rest, C plus A. Classifier 3 is C versus rest, A plus B. So let's say this is the classifier 1. So classifier 1 will be this A class and the rest B plus C all will be in some other class. So basically class A is the success and rest is failure. So that's how we'll train our classifier 1. Classifier 2 will be class B and rest. Class B will be success and A plus C, any of the rest of the classes will be failure. And classifier 3 is class C and the rest, A plus B. So that's how we will train multiple binary classifiers, and our final class will be the classifier with the highest score. So let's say if classifier 2 has the highest probability score, then our class will be class B. Next approach is using deep learning, which is widely used nowadays. So in deep learning, we use just one model, one single model, but this will be a complex model. We'll have input layers, several hidden layers, and the output layer. So output layer has one neuron per class. So as we have seen, we have three classes in our data set. So class A, class B and class C. For three classes, we'll have three different nodes or neurons in the output layer. This node or neuron will output the class A probability, this will output class B probability, this will output class C probability. So I will create a separate playlist for deep learning. So there I will discuss everything in detail, but here I am just touching the basic things. So, and also it uses softmax to produce a probability distribution. We'll talk about softmax in this video. Now output representations. So we have seen we have k classes, right, between 0 to k minus 1. We are using zero indexing for classes. So yi, the output will be any of the k classes ck. Now how do we represent yi or our output? So there are two ways. First one is the integer representation. So we can represent yi or model output with integers corresponding to the class indices. So if we have three categories, let's say cat, dog and cow, and the correct label is let's say dog, then the integer representation would be 1. So basically cat is 0, dog is 1, cow is 2, 0 indexing, and the class indices will be our output representation. Next representation that is mostly used for model training, that is the one-hot vector representation. So we can represent yi or model output with a k-dimensional one-hot vector. So this is a k-dimensional vector, and here in one position only we'll have 1 and the rest will be zeros, and this will represent the kth class. Wherever we'll have 1, so that will represent our class. So let's say if out of 4 classes the true class is 2, that is 0 index, so there are 4 class 0, 1, 2, 3 and true class is 2, so it will be 1 at position 2. So that's how we'll represent our output class. Now how to calculate the class probabilities? So in binary classification, we train for only one set of W or weight vectors, right? So it was a D plus 1 dimensional vectors, and for k classes, basically then we have to train k weight vectors, because earlier we were just doing binary classification 0 and 1, but here we have k classes, so we need k weight vectors. So W0, this is W00, W01 till W0D. So this upper script in bracket, that is basically is for the class. Here I am representing. W 1, that is for the first class, the weight for the first class. So that will be W10, W11 till W1D. Similarly, till Wk plus k minus 1, it will be Wk minus 1 0 till Wk minus 1 d. So these are the weight vectors for k classes. Now let's take any input xi. So that will be a d-dimensional vector, right? And output yi will be any of the k values 0 to till k minus 1. Let's convert the yi into one hot vector representation. So we get yi0, yi1 till yik minus 1. So any of these values will be 1, rest will be zeros, and that 1 will represent the class. Now we have to calculate the probabilities for all the classes. Given any xi, given any input xi, we have to calculate the probability for all the classes. How we will calculate the probabilities? First, let's say we have the weight vectors for different k classes, right? So using those weight vectors, we'll get some linear continuous outputs, and then we can convert those continuous linear outputs to probabilities. So let's say first we are getting this AI, that is W0 transpose Xi, W1 transpose Xi till Wk minus 1 transpose Xi. So for all I in 1 to n. So what is W0? So that is the weight vector for class 0. W1 is weight vector for class 1. Wk minus 1 is weight vector for class k minus 1. So W0 transpose Xi, that is basically the value we computed for class 0. W1 transpose Xi, that is we computed the value for the class 1, and so on. Now next we have to convert these values into probabilities, because these values we got, these are not between 0 and 1. Now how do we convert this linear values to probabilities? That's when we'll be using softmax. So let's first see what is softmax. So let's say if we have this values R0 till Rc minus 1 for R. So we are computing softmax for any Ri's. That will be e raised to the power Ri divided by summation for all j equals to 0 till c minus 1 e raised to the power Rj. So if you see this summation part, j equals to 0 to c minus 1, basically we are considering all the c values, right? For all the c values, we are computing e raised to the power Rj. We are taking the summation, and that is the denominator, right? And the numerator is e raised to the power Ri. So for softmax, Ri is basically computed using this formula. Here E is the Euler's number, and this output, this will be the probability and it will be between 0 and 1. So this softmax of Ri, that will give the probability of any of the classes. So in our example, we found this AI, right? That is W0 transpose Xi till Wk minus 1 transpose Xi, few values. These are not necessarily any probability values. It can be negative values, it can be any other continuous values, right? So AI of k is basically, let's say for any class we are taking the values, that is AI k, that is Wk transpose Xi. Okay, so now this values, basically we have to convert this value to some probability using softmax. So let's say we are taking Zik, that is softmax of Aik, which is e raised to the power Aik divided by summation j equals to 0 to k minus 1 e raised to the power Aij. So that's how we got this Zik. That will be the probability for kth class. So now this is the softmax function we saw. Now why do we use the softmax? Softmax will squeeze the probability values between 0 and 1. Let's see why. So e raised to the power minus infinity is 0, e raised to the power infinity is infinity, or e raised to the power any value is basically greater than 0, right? So e raised to the power any values, this will be a positive values. And what we are doing here, e raised to the power aik, that is for kth class, and these values are for all the classes, right? We are taking summation for all the classes and only for this particular k classes. That's how it is giving the probability, that is between 0 and 1. Next thing is, this exponential, this is actually amplifies differences. Exponential magnifies larger values. Like if aik greater than ail, then e raised to the power aik is much greater than e raised to the power ail. So this helps the model assign higher confidence to the correct class. Now, this values, probability values, basically we have computed. So we had this W0 transpose xi, W1 transpose xi till Wk minus 1 transpose xi. These values we computed using the weight vectors. Then we took the softmax of that. That is basically softmax of ai0, softmax of ai1, till softmax of aik minus 1, and that is zi0, zi1 till zik minus 1, which is zi, this vector. And these are the vector containing the probability for all the classes. Now, the summation of all these probabilities will be 1. Summation. Next, let's talk about the loss function or the cost function. How do we derive that? So, the probability assigned to the correct class will be like this. So, let's say that is probability of yi given xi. So, these are the probabilities we calculated, right? zi0, zi1 till zik minus 1. So, these are the probabilities for k classes. So, what is the probability that is assigned to the correct class? So, that will be any of these k classes, any of the k class will be the correct class. So, it is zi0 if yi is this 100 transpose, this vector, right? Or yi0 is 1. So, that means in the actual output, in the output given in the data set, if the output class is 0, then zi0 will be the probability of the correct class. If if yi is 0, 1 till 0 transpose, this is the vector, then or yi1 is 1, that means if the actual output class is 1, then zi1 will be the probability assigned to the correct class, and so on. So, we understood this. Now, this we can represent as this formula. Probability of yi given xi is zi0 raised to the power yi0. So, basically we are raising zi0 raised to the power yi0. Then zi1 raised to the power yi1 till zik minus 1 raised to the power yik minus 1. Why we are doing that and why this works? So, any of this yi0 till yik minus 1, any of this will be 1, rest will be 0, right? So, if let's say this is the actual output is 1, right? So, yi1 is 1 and yi0 or any other yi values will be 0. So, anything raised to the power 0 is 1. So, this values will be 1. So, we will just get the value zi1. So, if yi1 is 1, then we will just get the value zi1. If yi0 is 1, then only yi0, this will be 1, we will get zi0. Rest will be 1. So, that is why this probability, this formula works. Now, this is the probability of getting the correct output and we call it likelihood as well. So, let us simplify this. So, it is basically the product of k equals to 0 to k minus 1 zik raised to the power yik, and this is the likelihood. So, this actually is basically what? Zik, any zik where k is the correct class, where yik will be 1. Right? So, it's basically zik where k is the correct class. So, this is the probability or this is the likelihood of the correct class. So we have to maximize the likelihood, right? So, or we maximize the log likelihood. So if we take the log of this p of yi given xi, that is log of this thing. So log of this product will be summation of k equals to 0 to k minus 1, and log of this is yik log zik. So this is our log likelihood that we have to maximize. Instead of that, we can minimize the negative log likelihood, that is loss is minus li. This is minus of this summation k equals to 0 to k minus 1 yik log zik. And this thing is called cross-entropy. And that we use in our gradient descent. This loss function we use in our gradient descent to optimize and get the optimized W weight vectors. Now, why it is called cross-entropy? What is entropy? Let's say probabilities of our k classes are P0, P1 till Pk minus 1. So, entropy will be minus summation k equals to 0 to k minus 1 Pk log Pk, right? But here we see this yik, this is the actual output, zik, this is the computed output. Right, so these two are different. In entropy, both were same. Here it is different, and this is called cross entropy. Then that is the loss function for multi-class classification. So this is the loss function we found, that is for EI, that is for any x size, right? So if we get the total loss over n samples, that will be E over W, that is summation of I equals to 1 to n. For all the data samples, we'll get the loss. And that loss we'll use in our gradient descent formula. This is the loss function that we will use. We'll take the gradient of that and we'll do our gradient descent updates to get the optimized value. Now next, let's discuss about categorical cross-entropy and sparse categorical cross-entropy. So these two types of loss function or cross-entropy loss functions we use usually. So categorical cross-entropy is used when it requires the target labels to be in one-hot encoded format. Sparse categorical cross-entropy is designed for cases where the target labels are not one-hot encoded. The labels are represented as integers corresponding to the class indices. So, internally, the integer labels are converted into a one-hot encoded representation before computing the loss. So this method reduces memory usage and computational overhead, especially for datasets with a large number of classes. So sparse categorical cross-entropy is used when we just have the integer representation of the outputs, but it is actually good for memory usages and all, but internally it converts the output to convert the output into one-hot encoding. Now inference, so the last thing we'll discuss about the inference, which is during test time, how we'll get the class for any new data. For any input text, we'll predict output class as follows. So we got the, we optimized our model, we got the weight vectors, and we'll calculate the probability for k classes, right? So z equals z0, z1 till zk minus 1. And that is softmax w0 t transpose x, softmax of w1 transpose x till softmax of wk minus 1 transpose x. All the probabilities we got, and whichever probability will be higher, that will be our correct class. So output class k star is basically argmax of zk for k equals to 0 to k minus 1. So that is how for any new data will be calculating, will be finding the correct class.